Swayam Prabha. Digital India. Educated India.
So, I welcome you all to this course on steel making. This course, which comprises of nearly 40 lectures, will be delivered by myself, Professor Deepak Majumdar and Professor Satish Chand Korea. Both of us are working at IIT Kanpur for a long time and specialize in steel making. And throughout this course, our objective has been to provide adequate knowledge on steel making to you, such that you can appreciate the relevance of the subject in present context, understand its wide knowledge base, and then think that how developed the subject is and how difficult it is really to make further improvements. Today, when we talk about steel making, we understand that it is more than nearly 150 years old, near perfect technology, enormous casting rates, enormous steel making and primary steel making vessels, and highly clean and sophisticated grades of steels. So, we have advanced remarkably, and doing further improvements to steel making certainly is not as simple as in many new fields which have emerged in recent years. So, it is therefore necessary that you have adequate knowledge of the subject, you have adequate knowledge of the fundamentals, and it is with this adequate knowledge and fundamentals we think that you should be you will be eventually a better steel maker, a better steel making engineer, or a steel making metallurgist, as we say, and will be able to contribute immensely in the field of steel making. Now, as I have mentioned, we will deliver lectures about 40 hours. Sometimes you will see me, sometimes you will see Professor Korea. We will deliver lectures on diverse topics, which will encompass fundamentals, which will encompass primary steel making, secondary steel making, casting processes, electric arc furnace steel making, BOF steel making, continuous casting, you name it, and we will be delivering lecture on practically all aspects of steel making. So, this being the first lecture, I will start the discussion with an overview of the subject, which is sort of general. I intend to give you a historical perspective first, and followed by that I will give you an overview, which is a broad sketch of the steel making circuitry, and examine in details the issue of energy in steel making, and finally I will wrap up this two lecture section by making certain statements regarding the future of steel making, what was yesterday, what is today, and what will be tomorrow like for all of us. Now, as you are aware that steel is a very old material and known to mankind for a long time, and today you look at any area, be it automotive sector, railway sector, construction sector, everywhere you find steel is there. And what is steel to us as a metallurgist? Steel is a solution of carbon in iron with certain amount of trace elements, maybe sometimes silicon, sometimes other alloying additions like manganese, and occasionally we have some impurities also present in steel, which we are unable to drive off completely. But from an engineer's point of view, steel is a material which has diverse properties, and these properties which come to our use are mostly, we are talking about engineering properties, and steel has, as you know, excellent toughness, good tensile strength or strength. It has good strength to weight ratio. It is basically, I would say, can withstand thermal high thermal environment or high temperature environment. It has immense recycling potential. You imagine you have iron ore from the mines, and then you make iron, and eventually that iron becomes iron ore. It corrodes and it gets back into the soil. So it has many qualities which has made it attractive, but most importantly is the wide range of mechanical properties. And these mechanical properties we have been able to induce into steel by virtue of a proper melting circuitry, a proper refining circuitry, and finally by a series of mechanical working processes whereby we control the microstructure of steel and induce into steel a variety of properties. Now, steel is made, as you all know, either from the blast furnace iron making, of course, you must have done prior to this particular course. So, molten steel, molten iron which we produce in blast furnace, which is known as the pig iron. So, we can have a pig iron based or blast furnace based iron making, a steel making process. Alternatively, we can have a DRI based steel making process also. Okay. So, blast furnace based steel making, I will write it like this: blast furnace based steel making based or pig iron based steel making. And then we have DRI, which is called direct reduced iron, DRI based. DRI based steel making basically does not require, often do not require molten pig iron. So, it is supplemented with some amount of scrap, maybe sometimes some amount of solid pig iron, and pig iron based or liquid pig iron based, this I would say better, liquid pig iron based, because some plants do use solid pig iron charge also, and DRI based steel making processes often uses plus scrap plus solid pig iron. So, liquid pig iron based steel making processes essentially are the oxygen steel making processes, which we say as basic oxygen steel making process. On the other hand, DRI based steel making processes are termed as the electric steel making processes or electric. The furnace in which BOS is carried out is termed as the BOF, basic oxygen furnace. The furnace in which electric steel making is carried out is the electric arc furnace, as we all know. Once we produce steel, which is we call as the crude steel, we have a series of secondary refining operations, and following the secondary refining operations today, what we have is continuous casting. As you all must be knowing that ingot casting has been phased out. Of course, in certain specific areas we have ingot casting still practiced, but very minuscule level. More than 95% of the world steel produced today is cast through continuous casting process. Today, a steel plant based on ingot casting with BOF steel making is not sustainable at all, because the rate at which the basic oxygen steel making process produces steel, it requires an equally fast process to convert molten steel into solid product. So, ingot casting is a much more slower process. The conversion rate from liquid to solid is much slower in ingot casting than in continuous casting. So, ingot casting is no match for BOS. So, with BOS or BOF, we require what is we call as continuous casting of steel making. So, with basic oxygen steel making process and ESP or electric steel making process, we have a series of secondary steel making process. We will discuss this, and as I said, a variety of secondary steel making processes, and all the secondary steel making processes are not used to produce a given grade of steel. They are basically used depending on the requirement of the customer. This will be clear to you in a moment. And following that, we have continuous casting. Now, what is the history of steel making like? When was steel first made? So, more than 150 years ago, and the father of steel making is Sir Henry Bessemer, a British engineer who first in a clay crucible used a clay tube, fire clay tube, to blow in air through molten pig iron, and that's when steel making really started. And since the days of Henry Bessemer, remarkable advances, as you all know, have been made. So, we first started with what is the process known as the Bessemer process. We had the Thomas process, we had the open hearth process, and gradually these processes, they were phased out by 1960s or 70s completely. Today, basic Bessemer process of steel making is virtually non-existent, or Bessemer process of steel making. Similarly, Thomas process of steel making, which also involves blowing of air through molten pig iron, has also been nearly phased out by 1970s. Open hearth steel making is remaining in one or two places all over the world, and today bulk of the world steel is produced by two different routes, which is the basic oxygen furnace and electric arc furnace. Now, the remarkable production of steel has been possible in the last 50 years or 60 years because of the advent of oxygen steel making process. And the first oxygen steel making process, which is known as the LD steel making process, started about in the era of 1950s, late 1950s, in a place called Linz, places called Linz and Donawitz simultaneously near Austria. And since then, the production of steel really surged quite a bit, and it is after the Second World War really there is a lot of scrap also available, and simultaneously how to convert that scrap into a meaningful value added product. So, the electric arc furnace also picked up momentum. Today, if you look at the production of steel, we would say 60% of the world crude steel is produced through the basic oxygen steel making process. On the other hand, about 34% of the world steel is produced the electric arc furnace steel making process. Last year in 2008, for example, how much of steel was produced? Almost 1,330 million tons in 2009. Enormous amount of productivity, because everywhere the whole world is developing. There are countries like India and China where a lot of construction has to take place, and we have large population in these countries. So, the global demand for steel has increased remarkably over the years, particularly during the last 3 decades and so on. So, if you look at the quantum of steel that we have been able to produce in the last 50-60 years, almost 5 to 6 times more steel are being produced today. So, if you talk of 1950s, 1960s, we were producing something like say 200 million tons, and today we are at almost 6-fold increase in the last, from 200 million tons around 1950-60 to about 1,330 million in 2009, which essentially tells us that has nearly about a 6-fold increase, 6 to 7-fold increase in the, and that the society needs now more and more steel because development work has to go on. People lifestyle has increased, and actually, if you all know that the consumption of steel is an index of the wealthiness of a nation. I mean, because you see, steel is used to produce automobile, steel is used to produce refrigerator body, steel is used to make fans, air conditioner bodies, and so on. So, high consumption of steel necessarily tells that people have a lot of money in their pocket and they are able to buy all these kinds of gadgets for their comfort. So, therefore, a society, if it consumes more and more steel, we will certainly see that, certainly find that yes, that society is a very developed society. People have a lot of income and they can spend money in many items, the backbone of which essentially is steel. And indeed, the consumption of flat products means, as we will see later on, steel is produced in the form of, say, long products. Long products is what? Railways, for example, rail lines or rail tracks that you see, many plants produce that. So we say it is a long product plant. Okay, wire and rods which are used in the houses. So these are all long products. On the other hand, flat products are out of slabs and sheets, and ultimately thin sheets or strips are produced by rolling. And we say that if a plant produces, you may have seen huge trucks moving on the road with strips of steel in the form of a coil. So how are they produced? They are produced from continuously cast slab, and then the continuously cast slab is rolled, and then you produce thin strip. So these flat products, if a society consumes more flat products, that means the society must be building in more automobiles, the society must be making more trains, the society must be making more fridges, more household washing machines, household equipments, and so on. So the consumption of flat products or steel flats are again an index of the wealthiness of a nation. Okay. So remarkable increase has taken place in the arena of steel production, and this has been possible because of widespread development, application of knowledge on shop floor, developments of newer technologies, new sensors, and all these things have paved the way for enormous production of steel. And today, if we look at the steel making circuitry, the way Bessemer made the steel, and today the way steel is being made, the number of human hands required to produce per ton of steel, the level of automation, the level of process control, they are remarkably different than what have been practiced 100 years back or since the time of Bessemer. So steel making now, since the days of Bessemer, for example, I have mentioned about Bessemer steel making. Thomas process, then we have open hearth process, which face now extinction. Now this process are open. Bessemer and Thomas processes use air as the oxidizing agent, because in those days there was no means to obtain pure oxygen. Bessemer did recognize that it is not correct to blow air. It is, in fact, he knew that perhaps it is better to blow oxygen, but in those days there was no source of cheap availability of oxygen was a big issue, and there was no commercial processes available. So he had no option but to blow in air. And today we know that nobody would, because oxygen is available, so using of air as an oxidizing agent is not really desirable. Now, if you look at pig iron composition, the pig iron contains, for example, approximately 4.48% carbon. It can contain various types of, it will contain some sulfur, it will contain some phosphorus, it will contain some silicon, it will contain some manganese, it may contain other elements, and oxygen virtually is 0 percentage, less than 1 ppm, because blast furnace has an extremely reducing environment. Now the level of sulfur, the level of phosphorus, the level of silicon and manganese which is there in the pig iron, which flows out from the blast furnace, depends on the raw materials which are used in the blast furnace and the operating conditions in the blast furnace. For example, you have heard this, that if the blast furnace is operated, blast furnace hearth temperature is very, very high. In that case, I would expect that the level of silicon contamination of the pig iron is going to be relatively large. Similarly, if I say that, well, if blast furnace slag basicity is not optimum, in that case sulfur level can be very relatively large. So, depending on the raw material composition, depending on the blast furnace operating conditions, the level of sulfur, phosphorus, silicon and manganese can vary significantly. For example, this could be silicon could be of the order of 1 weight percentage, manganese could be of the order of 1.5 weight percentage, sulfur could be of the order of 0.15 or 0.12, and in blast furnace we have no phosphorus removal, so the phosphorus could be about 0.15 and so on. Now, when we talk about crude steel, in this crude steel which flows out of primary steel making, we can have carbon less than 0.1 percentage. We can have lot of oxygen now, because it is an oxygen steel making process, and so the level of oxygen contamination could be as high as 400, 600, 800 depending on again the process. If you are pumping in too much of an oxygen, note that the solubility of oxygen in molten pig iron at 1600 degrees centigrade is about 0.2 weight percentage, which means about 2000 ppm of oxygen can go really inside steel, but it does not happen so. So, the level of contamination can be 400, 600 and the operator can control it. So, we can have say 400 to 600 ppm oxygen, and as I said, this is no sacrosanct value. This will depend on your the operating conditions. Now, sulfur and phosphorus can be get down 0.02 in the primary steel making process. In the phosphorus also you can get down to 0.008. Silicon can be 0.1 weight percentage, and so on. If you take secondary steel making, it is possible to reduce oxygen level. You can have nitrogen also, and nitrogen could be 40 to 80 ppm. Where from the nitrogen comes? Nitrogen is absorbed during tapping operation. So, when you empty the furnace, the molten steel comes from the furnace and falls into the ladle. It interacts with the ambient atmosphere, and thereby oxygen passes, nitrogen passes into. Sometimes, if you have moisture in the environment, or if your raw materials are hygroscopic, you can have some hydrogen pickup also, and the level of hydrogen could be 2 to 5 ppm depending on the plant conditions. So, to remove, as you see, phosphorus, silicon, manganese, carbon, the removal of this, you will study this in detail and the principles of steel making. They have higher affinity towards oxygen. We will also, in the Ellingham diagram that I will discuss when I talk about the science base of steel making under the section of thermodynamics, we will see these are the elements carbon, phosphorus, silicon, manganese. They have great affinity for oxygen, and that is why when you pump through molten pig iron oxygen, what happens is that this element reacts with oxygen and gets oxidized. So, steel making basically is an oxidizing refining process. You introduce oxygen and thereby you refine the impurities which are present in, or elements which are present in the pig iron itself. Now, if you introduce oxygen, for example, air, for example, you can understand that this air is going to have nitrogen in it, 73%, 79% nitrogen, 21% oxygen. So, therefore, the contamination of steel produced with nitrogen is going to be very, very large. Also, we must know that while blast furnace iron making depends on a fuel, because we have to meet the thermal requirements of many endothermic reactions which take place in the blast furnace. The oxide reduction reactions are all endothermic reactions. So, where from the heat is going to come? The heat comes through combustion of coke into carbon monoxide, and that melts, reduces iron ore and helps to melt solid pig iron, or sponge iron in the liquid state, or bring it into the liquid state. So, we have in the blast furnace external heat source, which is, or the burning of the fossil fuel, which provides the necessary heat. On the other hand, in steel making, we do not require any external heat source. Steel making is an autogenous process, which means the oxidation itself produces so much of heat that it is enough to bring steel at a temperature of about required temperature over 1580, 1590 or around 1600 degree centigrade. So, a threshold amount of carbon, a threshold amount of silicon is necessary to produce that desired level of heat, because in the steel making reactor also we have to supply heat for many jobs. For example, lime dissolution, slag formation, okay, these will necessarily require heat. Where from the heat is going to come? The pig iron, what kind of a temperature it is tapped? It is taken out of the blast furnace maybe about 1300 degrees centigrade. Again, this may vary 1350 or so. On the other hand, we have steel making at 1600 degrees centigrade. So, after we have supplied heat for all endothermic processes, for entire mass we are going to jack up the temperature by 1600 degrees centigrade. So, therefore, it is understood that if it is an autogenous process, if the heat liberated in steel making is because of the oxidation of carbon, because of the oxidation of silicon, because of the oxidation of phosphorus and manganese, we have to have some critical amount of these elements present in the pig iron. Otherwise, it will be very difficult to bring it to 1600 degrees centigrade. Often in steel making, we will see that the level of contamination is such that the temperature gets even more than 1600 degrees centigrade, and that is why when such a scenario we experience, we add coolant into steel, which is nothing but the plant generated solid scrap, and that solid scrap, when you put into the steel making reactor, the temperature goes down. So, coolants are normally used, but what is important for us to know is that steel is an autogenous process. Now, when you use air, you are pumping in more amount of air, because the air contains, you require some threshold amount of oxygen to get into that, to get that much oxygen pumped into molten metal, molten steel. Okay, you have to pump in more amount of air, because air contains only 21% of oxygen. So, therefore, it is understood that more volume of air is going to be introduced. More volume of air, if it is introduced, that means more heat is going to be consumed by the cold air, and then you are introducing more amount of nitrogen because of that, and this nitrogen is without doing anything going out of the steel converter. Therefore, it is going to take away heat. So, the material, so in the Bessemer steel making process, because of this thermal requirements, you require a critical amount of phosphorus, a critical amount of silicon, such that this critical amount of silicon and phosphorus may offset the requirement or may fulfill the, I would say, fulfill the thermal requirement of the process. Otherwise, if you do not have a critical amount of phosphorus and silicon, in that case, so much of heat is going to be lost because of high volume of air injected, that the steel may not be at the desirable temperature. And that is why, even though people knew that air is not a good oxidizing agent, okay, you cannot produce dead soft steel or a very low level of carbon in the steel with air. So, therefore, there is always steel makers always wanted in the beginning to produce or to make steel through an oxygen steel making route, which was not possible since late 1950s, when the LD steel making process was encountered. Open hearth process, this is a pneumatic steel making processes. Okay. Now, steel making processes, as you all know, can be classified into acid steel making process and basic steel making process. In acid steel making process, for example, the slag is acidic. That means acidic means the basicity is less than 1. You know already the definition of basicity. So, basicity is less than 1. So, the pig iron having more silicon, and therefore, less phosphorus, and you can, because removal of phosphorus, as we will see, will require high basic slags. Removal of silicon may not require basic, if phosphorus is not there, you can make silica, oxidize silicon to silicon dioxide, fix it with iron oxide, produce a ferrous silicate slag, and that we will be calling as acid steel making process. Acid steel making process, the converter lining is going to be acidic also, because if you have slag as acidic, in that case, if the lining is basic, then the slag is going to eat up that lining, and the vessel will require frequent relining, which is not desirable. So, in the case of basic steel making process is going to be used when charge contains more phosphorus and less silicon, particularly in the context of basic steel making, basic Bessemer process. So, in basic steel making processes, you have slag basicity more than 1. So, you can afford to have the lining of the reactor also as basic. If you make the lining acidic, then the slag is again going to eat up the. Today, acid steel making process nobody practices. The steel making processes are all basic, whether it is electric arc furnace steel making process, ESP, or whether it is VOS. It is always basic oxygen steel making process, because by making a slag with high basicity more than 2, 2.5, 2.8, etc., it is possible to simultaneously eliminate both phosphorus and silicon when we particularly inject oxygen to the system. So, coming back to the history of the steel making. So, air has problem, acid steel making was not practiced, acid steel making process, which is Bessemer steel making, basically phased out. The basic Bessemer process has also been phased out now, and the open hearth process is not a pneumatic process. So, these are in the bottom blown converters. So, through the bottom of the converter, we in a vessel, converter is nothing but a pear shaped vessel in which steel is made. So, we have set of tuyers through which air was introduced. So, these are pneumatic steel making processes. So, the air, you have a molten metal here, and as the air is introduced, then there is going to be complex convection current here, and this expedites the rate of reaction which are essential of the steel making process itself. Open hearth steel making process, on the other hand, as the name suggests, the hearth, you have a big hearth, wide hearth, and that hearth is open. It is basically there is no oxygen injection in the original version of open hearth furnace. Then how is the pig iron going to be oxidized? The pig iron is going to be oxidized in the open hearth process. The oxidizing agent is the iron ore. There is very little agitation in the open hearth furnace. Okay, and as a result of which, what happens? The rate of the reaction, steel making reaction, carbon plus oxygen, sulfur plus calcium oxide, phosphorus plus oxygen, silicon plus oxygen, all these reactions, as we will see later on when we talk about the fundamentals, these are mass transport controlled processes. They depend on the level of agitation. So, in the open hearth process, because we do not have much agitation, because we have no oxygen pumping through the open hearth furnace, we have oxygen is supplied from the iron ore, and that oxygen which is present in the iron ore will react with phosphorus with silicon, then become phosphorus pentoxide, silicon dioxide, and then they will react with lime in the slag and form calcium silicate, calcium phosphate, and so on. But that the level of agitation in the open hearth process is small, the rate of steel production is extremely weak. Okay? So, relatively slow rate of open hearth process is responsible for its losing of popularity, and therefore, later versions of open hearth processes involve some kind of an oxygen lancing also. But today, certainly with oxygen steel making processes, we are better off. So, we really do not have to consider all these things. Okay? So, these processes have many demerits with regard to the present day steel making technology, which is oxygen based. And as we will see, as I discuss, give you an overview of the oxygen steel making, you will be able to understand that how does these processes compare vis-a-vis the productivity, the wide range of quality that are today possible through oxygen steel making processes. Now, let me give you an overview of the modern. So, this is overview of the modern steel making process. So, I think if you are interested to know about the subjects of this in more greater detail, there are textbooks available where you can refer to, but in the present context, perhaps beyond this, it is not important for us to go beyond this depth. Now, when we talk of modern steel making process, we are talking of the era of oxygen steel making. That means we are talking of the post 1950 years, and we are talking of steel making that is mostly the oxygen steel making processes. Now, as I have mentioned, today we have 60% of steel through basic oxygen furnace and 34% of steel through electric arc furnace. And I do not write basic arc furnace because steel making today per se is basic steel making. So, we have a lime rich slag which is there. Now, remaining 6% what is there, this could be many industries like induction furnaces, open hearth furnaces, a few of them which are available. So, they rest other processes, induction, open hearth, etc., fill in the gap and make it 100%. So, we have primary steel making. So, the steel making today we divide it into 3 different categories. We will say we have primary steel making, we have secondary steel making. I myself do not like the name of secondary steel making, as if it is secondary, it is not so important, but as I will we will see in this course that secondary steel making today is the heart of steel making. It is here that the finest quality of steel is going to be produced. It is here we are going to ensure that what kind of a future product, steel certified steel product we are going to deliver to the customer. So, this is per se the most important part of a modern day steel mill. So, I do not wish to say secondary steel making, although this terminology is very common in industry. So, I will call it as a ladle metallurgy steel making. That will be my terminology, ladle metallurgy steel making. And finally, we will say casting, and when you talk about casting, we talk about primarily continuous casting. So, this is basically the components of a modern day steel making circuitry. And when you talk of primary steel making, we have 2 predominant routes of primary steel making. So, this is number 1, which is 60% BOF and 30% EAF. So, let me now schematically draw this. So, we have, this is the basic oxygen furnace, and this is a schematic representation of a LD converter. The top lance here. Similarly, we have a schematic representation of an EAF. We show that we have 3 different electrodes here, and this is an EAF process. So, we can produce steel through this, and then common to this primary steel making process is our secondary steel making, and this is what is known as we have finally subsequently. So, this is number 1, what I have shown here is primary steel making, this is secondary steel making or the ladle metallurgy steel making. So, we have here transfer operation. We have a variety of secondary steel making or ladle metallurgy steel making process. Maybe I can show that we have a process, if it is necessary for the grade of steel to be produced, then we can have and we have here slide gates. This is an RH degasser. We will study this later on. The purpose of this is to eliminate, and then we can keep on eliminate gases, and we can still have argon gas marching. A variety of processes we will discuss. Following this, we have, so this is the vessel, which is the ladle. So material will be transferred from the BOF to the ladle, or from the EAF to the ladle, and then a series of, and then we have so this is ladle, this is tundish, and this is continuous casting. These are slide gates which controls the flow. So from the ladle the material gets transferred into tundish, from the tundish it gets transferred into continuous casting. And this is the slab which has been produced, continuously cast slab. And subsequent to this, so this is the third stage, which is the continuous casting. And again you see between the second and the third stage, what we have? We have transfer operations. Transfer operations. So steel making per se, we can say it comprises of a variety of processing operations. We are processing, okay, we are doing chemical treatments as well as transfer operations. And as we will see in this course, to ensure correct quality of steel, it is important that we have adequate understanding of the processing operation as well as the transfer operations. We cannot ignore the transfer operations. Don't ever think that the transfer operations are not important. They are equally important in order to ensure. And then comes the final stages, which are the mechanical working process. So we have, rolling mills. So we have so mechanical working, and we can have continuously cast slabs, can be put into reheat furnaces, can be put into soaking pits, can be rolled, can be galvanized. We say final finishing operation. So this is the overall broad view. And this is 1, 2, and 3. Now let me give you some idea about, of course you are going to deal about basic oxygen steel making processes. So BOF, EAF, ladle metallurgy, and continuous casting. Let me explain this circuitry during the next 1 hour or so that you get a nice overview of the subject of modern steel making. So what constitutes feed to the BOF? So this is a pear shaped vessel. And it is refractory lined, and as I mentioned to you that the refractory has to be basic, because the slag that is going to form here is going to be basic. We want to remove both phosphorus and silicon in the process. So, therefore, the lining is basic. This is a steel shell. The vessel can be rotated like this, okay. While we want to tap it, there is a tap hole somewhere located here. We will do the details of these constructions later on also. What constitutes the feed of this? The feed here mostly liquid pig iron, scrap, then we have an oxygen. So, you have a water cooled lance here. This lance basically is a vertical tube, and on that vertical tube we have attachments which deliver molten metal oxygen to molten metal in certain fashion. So, typically we have a 6-hole lance. We will study the lance design later on. For better interaction of oxygen and liquid metal, because we want oxygen is there in the gas phase, the oxygen has to dissolve in molten metal, and then only in the molten metal it can see the carbon which stays in the dissolved form, it can see the silicon, it can see the phosphorus and interact with them. So, the dissolution and these reactions are essentially important for the production of heat, because more is the carbon oxygen reaction, more is the phosphorus oxygen reaction, more is going to be the heat evaluation. So, therefore, the rapidity with which the slag is going to be formed will depend on how much of heat is going to be available, and this will directly be related to the dissolution of oxygen in the process. A multi-hole lance distributes oxygen and ensures that oxygen transfer from the gas phase to the molten metal is highly efficient. So, we have a cavity depression. This is, as I will discuss in the next section, there is an impinging gas jet. The gas jet is impinging on the surface, and the oxygen is introduced in a supersonic speed. That means the Mach number is greater than 1. So, once you introduce oxygen at a supersonic speed, tremendous amount of what happens, you can imagine, you take a, for example, a bucket full of water, and then you try to use a blower on the surface of it, you will see there is going to be a lot of droplets of water which are going to be ejected. And when you are injecting at a supersonic speed, you can imagine that you will create an enormous number of metal droplets suspended in the system. So, you create here a mixture of gas, slag and metal droplets, and you increase the surface area, and as I have mentioned, and you will also know in greater details, that steel making reactions are mostly mass transport control, heterogeneous chemical reactions, mass transport control, so they depend on the interfacial area. So, finer the droplets of metal is created, because where is the carbon sitting, where is the sulfur sitting, where is the phosphorus sitting, they are all in the metal. So, if you can create larger surface area, you will have a better possibility of the chemical to expedite the chemical reaction. So, therefore, when you inject oxygen at a supersonic speed, you create a large number of droplets, and that droplets produces larger surface area. So, the decarburization, dephosphorylation rates are very, very high. As a result of this, we can now imagine that the rate of steel making in such vessel is going to be extremely large. Okay? Carbon has good affinity for oxygen, so carbon oxygen reaction will be expedited, and we can have steel making, huge tonnage of steel can be produced within 30 minutes to 1 hour duration. What is the average kind of a decarburization rate we are talking about? We are talking about enormous, of the order of 10 kg of carbon per second. That is the rate of decarburization we are talking about. Now, these vessels can be of different sizes depending on the size of the plant. In some cases, you can find 130 ton vessel, but today there are plants which are 500 ton vessels, uses 500 ton only on water. Now, It is a highly expensive vessel. The relining, the bricks, fire bricks that we use here, basic bricks, they are highly expensive. So we would like to take this vessel not for frequent lining. Once we line the vessel, our objective would be to use as many blows as possible. So therefore, we want a very good or prolonged lining life. And therefore, today what happens is the economics of steel making is such, it demands that we should consider only decarbonization in primary steel making vessel. Forget about other adjustments like desiliconization. Silicon of course will get removed, dephosphorylation and desulfurization to a significant extent. Carbon will be eliminated, phosphorus can also be eliminated, but we will not bother too much about the level of oxygen or level of sulfur, we can remove that. So our major thrust in today's primary steel making vessel is to eliminate decarbonization. As soon as the carbon is eliminated, we say that, well, now we take the steel, we bring it to these processes, level metallurgy steel making, and there we adjust other composition, phosphorus, sulfur, etc., and so on. Now, to expedite the rate of reactions here, further we have combination blown steel making processes also, which is a version of the oxygen steel making process. In many steel plants, they use the combination blown steel making process. This does not mean that we use oxygen from the bottom. We use argon. A small amount of argon is used, and that argon produces, adequate amount of stirring, which expedites the process. We have also processes which are called bottom blown oxygen steel making processes or tube up process, okay, where we don't have a lance, but we inject oxygen from the bottom itself. And there, what we do, we use a coaxial tuyeres. Through one, we have two cylindrical cylinder shaped hollow cylinders which are used as tuyeres. So you have an inner cylinder and then an outer cylinder. Through the inner cylinder, oxygen is produced, oxygen is introduced. To the outer cylinder, hydrocarbon is introduced. Oxygen produces. If oxygen is introduced through the tuyere, in that case, enormous amount of heat is going to be produced here because of the oxidation reaction, and as a result of which the life of the tuyere can be significantly reduced. So hydrocarbon serves as a coolant. How? Hydrocarbon cracks, and the cracking is an endothermic reaction. So if you introduce hydrocarbon, of course, injection of hydrocarbon contaminates the bath with carbon. This is true, but to prolong the tuyere life, because if the tuyere life is less, in that case the furnace will need frequent relining, and that will jeopardize our principal objective of using this converter for how many hits? Today 20,000 to 30,000 hits. 20,000 to 30,000 hits each converter can sustain, okay, in progressive modern steel plants. So if you are talking of 30 hits a day, okay, in that case you can imagine that for 1,000 days the converter can last, and 1,000 days roughly means that you will require a converter to be relined only after 3 years of time. Once you line it, for 3 years you have to forget about it. There are techniques like today slag splashing techniques to prolong the further the life of the lining of the converter. So coming back to the bottom blown oxygen process, so we have hydrocarbon injection, that hydrocarbon cracks and produces locally endothermic reaction, and that endothermic reaction actually protects the tuyere. So we have various versions of the steel making processes. Mostly LD and combination blown steel making processes are being used, and these are very fast processes, and the main task here is to decarbonize the bath. And once we decarbonize the bath, we say that steel is made, and we must understand that along with steel, as we refine the steel, we produce also lot of slag here, which has high percentage of iron oxide. It is a highly oxidizing slag, because when you oxidize carbon, when you oxidize silicon, when you oxidize phosphorus, because iron is abundant, some amount of iron also oxidizes, and whatever oxidizes goes to the slag phase that you all know. So slag is basically slag is basically comprised of various oxides. We have added calcium oxide to fix silica, phosphorus, etc. It's a basic slag. So silica, phosphorus, silicon dioxide, phosphorus pentoxide, manganese oxide, calcium oxide, AFeO, they all constitute the steel making slag, which has a very high oxidizing power. And when we tap, so after steel making, blowing, we have we initially introduce oxygen, and then after some time we take samples to find out that how much of carbon is there, how much of, and then control the end blow period. Okay, based on that simple analysis, we have also sublands, and through this sublands, the sublands is immersed into molten metal, and subland sample is collected, and we know that how much of heat we have been, how much of heat is there, and what is the level of carbon content, carbon present, and based on that we adjust our final stage of blow, or fine tune the final stages of blow, introduce the requisite amount of oxygen, and then get the final composition of the melt in terms of, primarily in terms of carbon. And once that is done, we empty the vessel, and where we empty the vessel, we have a transfer operations here. We tilt the vessel and we pour it in a ladle. As we tilt the vessel, we must ensure that the slag does not get into the ladle, but we will require some amount of slag here to serve as a protective cover. So we will freshly make a slag. We will not want any oxidizing slag, which is called the carryover slag, and carryover slag is a very detrimental, as we will see as we advance in the course. Now, following we tap, as we tap, finish tapping, then the furnace is made vertical again. The operator inspects if there are any cracks or the lining needs repair or not. At that particular point we can have slag splashing also, and after that this, the preparation for the second heat and blowing starts. For the preparation of blowing is done, next blowing is done for the subsequent heats. Now, following that, we will have, this is, you will know much more details about the oxygen steel making process, about the details, but this much background is good enough for as far as this overview is concerned. And we can also have electric arc furnace through which we are going to produce steel. So the material which comes out of here, which goes into the ladle, now carbon is right, oxygen is not right, sulfur may not be also right, phosphorus may be okay, carbon is okay. So it will require further amount of treatment, because we have to get oxygen right, we have to get sulfur right, maybe nitrogen is also not right, because in the transfer operation nitrogen has picked up. So the steel which has come out is not the final steel that we want, it is a crude steel. It will require a variety of refining processes. Some gaseous species have to be removed, some further refining has to be done, oxygen has to be removed, and so on. So a variety of ladle metallurgy processes would be necessary. Now we are going to talk about the electric furnace steel making, and we will also see that what is the essence of an electric arc furnace steel making process.